To continuation of computations involving subgroups of symmetric group. And now, let us take A3, which you said has elements 1, the identity element, 1, 2, 3, 1, 3, 2. Now, let us denote as follows, okay? Supposing our maybe Z, so 1, 2, 3, and supposing our W, let me call it W or Y. So Y is our 1. Now let us do some little computation to see whether we have actually identify some order in this spatial group. For example, what is Z square? Z square is going to be 1, 2, 3 times another 1, 2. Let us do computations. What will it give us? Now this cycle says 1 is mapped to 2, and in the second cycle 2 is mapped to 3. 2 is mapped to 3. So ultimately 1 is mapped to 3. So we are going to write 1, 3. Now why is 3 mapped on 2 in the first cycle? So we say 3 is mapped onto 1. In the first cycle, 3 is mapped onto 1. In the second cycle, why is 1 mapped to? 1 is mapped onto 2 here. So ultimately, 3 is mapped onto 2. So 3 is mapped onto 2. Now 2 is our last digit. Why is 2 mapped onto in the first cycle? So we now come back and see. 2 is mapped onto 3 in this first cycle. In the second cycle, 3 is mapped back onto 1. So ultimately, 2 is mapped onto 1. That means 2 is mapped onto 1. So that means the cycle is complete now. 1 mapped to 3, 3 mapped to 2, 2 mapped back to 1. So now that means Z square is 132. But what is 132? 132 is our Y. Okay. So let us see what of Y square now. Y square is going to be 132. 132 times another 132. Okay. Now let us do our computation. We say 1 is mapped onto 3 in the first cycle, and 3 is mapped onto 2 in the second cycle, onto 2. So ultimately, 1 is mapped onto 2. So we now write like this. 1 is mapped onto 2. Now why is 2 mapped onto in the first cycle? 2 is actually a map onto 1. Now 1 is mapped onto 3 in the second cycle. So that means 2 is mapped onto 3. So 2 is mapped onto 3. Now why is 3 mapped onto in the first cycle? 3 is mapped onto 2 in the first cycle. And 2 is mapped back onto 1 in the second cycle. So ultimately 3 is mapped onto 1, so the cycle is complete. So we get 1, 2, 3. But what is your 1, 2, 3? It's Z. So it's going to give you Z. So what does this show you? It shows you that Z squared gives you Y. and y squared gives you z. Okay, so it means, therefore, you can now write, I can now write my A3 either as an identity element, then 1, 2, 3, what is my 1, 2, 3? Z. What is 132? Z square, isn't it? What is my Z square here? 132, okay? Z square. So it simply means that I can just say this group is generated by Z, okay? But that means it's a cyclic group, okay? This implies that A3 is a cyclic, one of the special features, cyclic group. Because I can also write it like this, if I like. Why? Instead of Z, I can pick the second one. What is my second? Y. Y is 132, okay? 132, okay? 1, 2, 3. Meaning that this is going to be 1, then y squared. Meaning that this group is also generated by y. So this means A3 is a special alternating group which is cyclic. Now, we can also test another property of this A3. Is it commutative? For example, what if I have zy, zy, is it the same as yz? You can test this. Now what is zy? Check. Zy is simply, what is our z? 1, 2, 3. What is our y? 132. Now multiply them. What do you get? This says 1 to 2, 2 to 1. So that means 1 to 1. So 1 is fixed. Now pick 2 now. 2 is mapped to 3 here, and 3 is mapped to 2 here. 3 is mapped to 2. So that 2 is also fixed. Now pick 3. 3 is mapped to 1 here, okay, in the first cycle. Okay, and 1 is mapped to 3 in the second cycle. That means 3 is also fixed. So this means this is going to generate an identity element. So that means Z times Y is going to give you an identity element. Now check what of YZ. YZ means you write Y first, that means 1, 3, 2, then Z. Z is 1, 2, 3. Check what it gives you. Now in the first cycle, 1 is mapped to 3. In the second cycle, 3 is mapped to 1. So 1 is mapped to 1. 1 is fixed. Take 2. 2 is mapped to 1 in the first cycle, and 1 is mapped to 2 in the second cycle. So 2 is also fixed. Take 3. 3 is mapped to 2 here in the first cycle, and 2 is mapped to 3 in the second cycle. That means 3 is also fixed. So this also gives you an identity element. This means what? YZ is also an identity element. So this shows you that ZY is the same as YZ in A3, which implies what? A3 is commuted. And what it shows generally is that A3 is a normal subgroup. Okay, A3 is a normal subgroup of what? ST. So you're welcome to the next presentation where we'll continue with computations involving special groups, subgroups of symmetric groups.